So up to this point, we've seen how to take some basic derivatives. We've also seen how to use the product and the quotient rule to take derivatives of products of functions and quotients of functions. In this section, we're going to talk about the chain rule. This allows us to take derivatives of composition of functions. And this is going to vastly expand our ability to take derivatives of functions. So let's start with just how we go about this. So let's suppose we have two differentiable functions, f of x and g of x, and let's set h of x to be the composition of them. So we're plugging g of x into the function f of x. So then in this case, the derivative of h is given by the derivative of f evaluated at g of x times the derivative of g of x. So let's go ahead and see some examples here. So let's start with a fairly simple example. So let's take the function h of x to be e to the 2x. So I'm going to use this notation h of x at first so we can say what f and g are until we get used to this. But you'll see pretty quickly that normally we'll just go back to using f of x for our function. You kind of have to just figure out what g and f are from context. So what is the derivative of e raised to the 2x? So we know how to take the derivative of e to the x, but when we put that 2 in there, it's a little bit different. So in this case, our inside function is 2x, and our outside function is e to the x. So notice if I plug in g of x into f of x, f of g of x is going to be e raised to the g of x, which is e to the 2x, which is exactly h of x. So we do have h of x is the composition of these functions. So now that we've written it as a composition of functions, we can apply the chain rule. So that means we're going to need the derivative of g and the derivative of f. So the derivative of g, since it's just 2 times x, is just 2. And we recall that the derivative of e to the x is just e to the x again. So then the chain rule gives that we should have the derivative being f prime of g of x, so e to the 2x, times the derivative of g prime of x, 2. So our chain rule gives us that this derivative is just 2 times e to the 2x. And we can also do this just using product rule, and we'll see that we get the same answer. So just by properties of exponents, we know that e raised to the 2x is e to the x times e to the x. Because when we multiply exponentials, we add the exponents. So x plus x is 2x. So we can just use the product rule to take this derivative. So notice that product rule would be derivative of the first times the second, plus the first times the derivative of the second. But we know the derivative of e to the x is just e to the x. So this derivative is e to the x times e to the x plus e to the x times e to the x. E to the x times e to the x is e to the 2x. And we're adding 2 of those together, so we get 2e to the 2x, which is exactly what we got using chain rule. So this gives us some verification that we're getting the correct thing in either manner. So let's try another example. So if we set h of x to be x to the 7th plus x to the 5th plus 2x raised to the 63, we want to find what is the derivative of this. Now obviously this is just a polynomial raised to some power, so theoretically we could take x to the 7th plus x to the 5th plus x to the 2x and multiply by itself 63 times and get some giant polynomial and then take the derivative of that polynomial. Obviously that's not the way we want to do this. We don't want to have to multiply that big of a polynomial out. So instead what we'll do is we'll use the chain rule. So we need to figure out what f is and what g is for this. So if we set g of x to be the x to the 7th plus x to the 5th plus 2x, and then we set f of x to be x to the 63, notice if I take g of x and I plug it into f of x, I get exactly h of x. So we've written this as a composition of two functions, which is going to allow us to use chain rule. Now, in order to use chain rule, we're going to need to know what the derivative of f is and what the derivative of g is. In this case, these are polynomials, so this is easy to do. So the derivative of g is just 7x to the 6th plus 5x to the 4th plus 2. And the derivative of f of x is just 63 x to the 62nd power. So now putting these together, if I put g of x inside of f prime of x, I have 63, and then I plug that g in, so I get x to the 7th plus x to the 5th plus 2x raised to the 62, and then I multiply that by g prime of x. Okay, now let's come back to an example we saw before where we said what we thought this derivative should be based upon doing some computations with some tables if we're looking at this exponential function. Now we can use chain rule to calculate what this derivative is exactly. So the first thing to note, and I mentioned this when we were saying what does this function even mean, is we can write b of x is the same thing as e raised to the natural log of b of x, because the exponential and the logarithm are inverse functions, so they're really not doing anything there. But then we can use properties of logarithms to bring that x out front of the natural log. So b raised to the x is the same thing as e raised to the x times natural log of b. And now in this situation, we can use chain rule. So if we set f of x to be just e to the x, and g of x to be x times natural log of b, again, we can write h of x then as just f composed with g of x. And now we'll apply chain rule. So remember that the derivative of f of x in this case is just e to the x. And notice that x times natural log of b is just some constant. So natural log of b times x, if we take the derivative of that, we just get natural log of b, because it's just really just the derivative of x. So when we plug that in, we get f prime of g of x is just e to the x natural log of b again. The derivative of b is just natural log of b. And now we just use that equality we had above in the reverse order, that e to the x times natural log of b is the same as b to the x. So making that simplification, we get that the derivative of b to the x is b to the x times natural log of b, which is exactly what we guessed it was when we were doing computations earlier. Now we do use here that the derivative of e to the x is e to the x. So we have to get that another way, but overall for the exponential, everything else follows from this. So let's just record this as another derivative that we know now, that the derivative of the exponential is natural log of b times b to the x. And so finally, let's consider a table with values given here for f and g and f prime and g prime. So let's suppose we set h of x to be f composed with g of x, and we want to calculate h prime of 1. So h prime of 1 by the chain rule is f prime of g of 1 times g prime of 1. And now we can read these off the table. So g of 1 is just given as 2, and g prime of 1 is given as 6. So we make those replacements. So I have that this is equal to f prime of 2 times 6. And then we go to the f prime column, and we see f prime of 2 is equal to 5. So we replace the f prime of 2 with 5. So we have 5 times 6. So this is equal to 30. And so this gives us our basics of the chain rule. We'll obviously see lots more examples and some applications of this in the regular lecture.